Today we're going to talk about arc length. So arc length is you have some kind of arc or path or curve, however you want to describe it, whatever word you want to use to describe it. We want to figure out the length of it. So in the real world, this would be like taking some kind of piece of string, and you might have it bent in different ways, but you can only straighten it out, put it on a ruler and say, okay, it's this long, right? But in mathematically, if you just have some curve and you have an equation or probably a parameterization that describes that curve, how do you measure how long that equation that curve is. So I'm going to go through conceptually the idea first of what we're going to do, and then we're going to turn that into an equation. Okay. So here's this curve C of t. C of t is the name of our curve, and it's we're giving it some kind of starting point t sub 0 and some kind of ending point t sub 1, and say we want to measure this curve when it starts here and it ends here. How far did you if you're imagining this like some kind of particle moving through space, how far did that particle move through space if we went from here to here? Or you could think of it as the piece of string, and then we're going to straighten it out and put it on a ruler, and that's what we want to measure. Well, we have it living here in three-dimensional space. You might say like maybe it's a piece of a circle, maybe we can use some kind of circle formula, but in general we can't guarantee that this is any way related to any other curve we've seen. It's just some kind of path in 2 or 3 dimensional space. In this case, we'll say it's in 2-dimensional space. So yeah, I'll draw that here. So this thing lives in the XY plane. So you have axes down here. So you have your XY space. So this is living in an XY in the XY plane. And you're saying, hey, I want to measure this length. We're going to start by basically estimating it. Okay. And so if we estimate just the straight path from here, from the endpoints, right, from T0, right? If we measure this, then this is some kind of estimate here, okay? It's a really bad estimate, but it is, after all, some kind of estimate. And so if we can figure out what exactly this estimate is, then we can start to get some kind of approximation for what is happening here. So if we can break this down into some kind to components here. So we can say, hey, look, there was how far it went in the X direction, and then how far it went in the Y direction, right? And so we can break this this distance up here into three parts, or into the length that we want, which is delta X and delta Y, right? So and then this length here that we want, which I'm going to label maybe delta S. We'll see. Maybe that will come up. No, I don't think that'll come up later. Maybe just the length here. The length is going to be the square root of delta X squared plus delta Y squared, right? Okay. Draw that down here. Okay. But we could have estimated this a little bit better by saying, let's just split the difference between T0 and T1, and say, okay, sometime in between here, we're going to take a, find some time, maybe the halfway time between. So if this is like from t equals 0 to t equals 1, then t equals 1/2 would be somewhere in here, right? And then you can say, okay, now I'm going to break up my curve into these two parts. So basically we have this part, this straight chunk, the straight chunk, and the straight chunk right here. Okay. And basically we could keep doing this. So if instead of putting it here, we could have broken it up into like 4 even chunks, and we can just keep breaking it up into finer and finer chunks and connecting those points with straight lines and measuring those straight lines using just breaking it down as a Pythagorean theorem problem, right? Because then if you just use all these, so the picture that I had on the first slide, right? All of these are, we broke up this blue curve into all of these green straight lines. And each of these green straight lines, we can measure using the Pythagorean theorem. Just how far did it go in the x direction? How far did it go in the y direction? And we get this sort of picture. And so these approximations are getting better and better as the changes in x and as the changes in t get smaller and smaller, right? So as we make these intervals smaller and smaller and smaller. So if you remember from calculus, that means we're taking a limit, okay? And as we take limits, as the change in time goes to 0, and we're measuring the change in x and the change in y, what we're really doing is taking derivatives, right? There's really some derivatives happening. So we take this and we say, let the changes in t go to 0, right? Okay. Cool. So if we do that, then we get a nice formula for the arc length here. I guess the other thing that I didn't point out is this L is just one thing here, but each of these would be a Pythagorean theorem, and then we'd have to add them all together. So it'd be like the result would be like a sum of a bunch of formulas that look like this, right? And so the total formula, if we're actually trying to do this, right? If we're taking a sum of a bunch of lengths of intervals, and we make that, and that interval length is getting infinitesimally small, right? We're sending it to 0. Then that sum becomes an integral, right? So you might remember this sort of pattern for how we did things in single variable calculus. So for the first time in this class, we're actually going to talk about integrals, okay? And the only time in this class we're going to talk about integrals, at least in a formal sense. And what we get is that if we want to compute this arc length, then we're taking the integral from t sub 0 to t sub 1. In other words, from the starting point to the end point of our path of the norm of the derivative of c. Now that doesn't look anything like what I was talking about before. But if you break down what that means, this is exactly the integral from t0 to t1 of the square root of x prime of t squared plus y prime of t squared dt, where all of this is, let's see, where am I? Where this x and y's business is just the components of this guy. Oh, there's an n here. I should be more careful about this. Yeah, according to the picture I drew, that formula would be correct. But we take c and we break it up into its component parts. So yeah, it's x1 of t, x2 of t, x3 of t, all the way up to xn of t. And so this formula should be the square root of x1 prime of t squared, and you add up all of the derivatives squared. So a little more complicated than what I originally wrote down, but what I originally wrote down would be like an example of this. So I'll write that here. When n equals 2, the length of the curve, so this is how we write it. We write L of C, it's the length of the curve, is the square root from t to 0 to t equals, from t sub 0 to t sub 1 of the formula I originally had, x prime of t squared plus y prime t squared. When n is 2, or when n is 3, I should say, the length of a curve is just the same thing, but with x, y, z. Okay. So this formula might look kind of complicated, but it should also bring to mind this the Pythagorean theorem, right? Because you're taking the square root of the sum of a bunch of things squared, right? Which is how we think of the Pythagorean theorem, at least in higher dimensions, right? And so this, at least in 2 dimensions, it should remind you of the picture we just had in the last slide, right? So we're just adding up this change in x and the change in y, and then this change in x and change in y, using the Pythagorean theorem to figure out this, then adding that to this. And then as we make those distances infinitesimally close, then it becomes an integral over this sort of picture here. Okay. Cool. Any questions on this formula? We're going to jump into some examples of using this formula in just a bit. But first, I want to highlight something. Well, first of all, this is the first time in this class, like I said, this is the only time in this class that we're going to actually be computing integrals at all, right? So far it's been pretty much just derivatives, derivatives, derivatives. Now we're suddenly introducing an integral. Now, if you look at this, right, it's a single variable integral, right? We're not going to get into multivariable integrals. That's what you'll learn in 10B. But for this class, this is still just a regular old single variable integral, right? It's from we're going from t naught to t. The only variable in here is going to be t. It's just going to be one variable. But we might need to bring out some of our skills from the last time you took integral calculus, okay? Which might not have been very recent. So the expectations aren't that you remember absolutely every formula you learned and every type of integral you learned. But you should know the basics. You should know, of course, the power rule for integrals. You should know use substitution, right? Using substitution for integration. You should kind of hopefully remember integration by parts as well. You should know those things so you can kind of use them in your arsenal. But notice that we're going to get integrals in a similar form a lot because we're taking a square root of a bunch of things squared. And so it's going to kind of put things in a certain form a lot. And so there's this nice formula that's going to end up coming up for you inevitably when we do this here. So here is a formula. Technically, you probably learned about it in an integral calc class. But this is the type of integral that ends up in the back of a textbook or on some sheet of common integrals we want you to know. So it comes, if you've looked at the homework for this section yet, which probably most of you haven't, but if you have, then you've seen that in a lot of cases, in a lot of problems, they say, hey, you might need this, okay? You might need to know this. They're basically just giving you this antiderivative and saying, use it however you want, okay? And so this is an important one to remember. I took some time yesterday to make sure that I knew how to justify it. So if you need to remember how to justify it, this comes from integration by parts. Integration by parts with u equal to the square root of x squared plus a squared, and dv equal to dx. Okay. With, okay. So if you want to brush up on your integration by parts, that's an exercise. But for the sake of this class and for the sake of this section, computing integrals, we're just going to give you this formula and just say, remember this formula, have it written down, right? For things like homework or quizzes or even the exam, right? The written part of the exam, or even, I guess, even the oral part of the exam. If we expect you to do some kind of integral, then first of all, I'm going to do it ahead of time to see how tricky it is, see if you need any, and if you need any extra formulas, such as this one, or any other type of formula from the back of the book type of thing that isn't too common, then I will provide it. Okay. So maybe I'll say that, write it down here so that you have it written. So any other formulas or integrals, maybe I'll say weird integrals needed for particular problems will be provided. That being said, I think this one should be enough to get you through most of the weirdness from this section. Okay, and I think we see it like right away. I think the first problem uses it. The first problem I have here uses it. But yeah, we didn't want to just throw you in and say like, here's a formula. Also, if you type this into Wolfram Alpha or some other integration computer, it doesn't give it to you in this form. It gives it to you in a slightly different form using hyperbolic sine inverse, which is, I think, not as nice as using the natural log here. Oh, also on the online homework, maybe that you've noticed this already on other homeworks, but the online homeworks likes to use log log for ln, and that's kind of common. So log, I think, when I first learned about logs, and whenever the log without any base meant log base 10, but in the online homework and in a lot of math textbooks, they like to use log to mean the natural log. Okay, someone's asking what is a, if it's a variable or constant. Yeah, this is just some fixed constant. Constant with respect to x. In general, for the sake of this section, that's just going to be a number. And also, this is I wrote it here with respect to x, but I think in the section it's going to come up mostly as in terms of t. So, but that doesn't change anything. Okay. Cool. Let's go ahead and let's do a few examples. Okay. We are going through this section rather quickly, so maybe we will get to 4.3 today. And I worked out my problems ahead of time today, so I shouldn't get stumped. Okay. That being said, if you have questions at any point, feel free to stop me or slow me down, whatever you need to do. Okay. There are the buttons, the reactions on Zoom. So if you don't even want to type in the chat, you can just hit the slow down button or something, and I should be able to see it. Okay, cool. So first example here, we have this path given by 2t comma t squared. So we're living in 2 dimensions here. And we're looking from the interval along the interval 0 to 2. Okay. So this is some kind of path living in 2-dimensional space. We can try to draw the path if we really want to, right? But we don't need to for this sake. We can just say, let's compute the length here. So first of all, we're going to need x prime and y prime, right? So x prime of t is 2, right? Just take the derivative of this with respect to t. And y prime of t is equal to 2t. Okay. Cool. So we have we can now just plug into this formula here, right? This formula here, because we're in dimension 2. So this is the integral. So the length of c is the integral from 0 to 2 of the square root of 2 squared plus 2t squared dt. Okay. Now I'm going to simplify this because so when I look at this, I see, okay, I see my variable squared plus some constant all under a square root. I'm probably going to end up using this formula. Looks like I'm going to have to end up using this formula. But it's not exactly in this form, right? It's not exactly my variable squared plus a squared. Now I could try to get away with maybe using some u substitution, like let u equal 2t, and then right, du is equal to 2d dt, and so you can rearrange stuff and make all this work. But I'm just gonna factor out, I see a 2 squared and a 2 squared. I'm gonna kind of factor that out. And so I get the integral from 0 to 2 of the square root of 4, which is that 2 squared, times 1 plus t squared. Okay. dt. Right. All I'm doing is saying, okay, this is 2 squared, which is 4 plus 4t squared. Right. Factor out that 4. And now the square root works nicely. I could pull the square root of 4 and then square root of this, and then move the square root of 4 would just be a constant. So I just get that 2 on the outside, and it go from 0 to 2 of the square root of 1 plus t squared dt. Okay. Okay. So now, according to my nice formula on the previous slide, this one here, this is going to be 2 for this 2 comes down here. And then I get times this integral, which according to this formula starts with a factor of 1/2 times, that's going to be nice. Those are going to cancel. T square root of 1 plus t squared. So in this case, 1 is just 1 squared. So a in this formula is equal to 1 plus the natural log of t plus square root of t squared plus 1. And this is going to go from 0 to t. Now, notice that the a squared, there's an a squared in front of the ln, but in this case, that's just 1. So I didn't write it here. Okay. So what would have been the hardest part, which is computing the integral, in this case is just that nice little formula. So we get some simplification happening here. The 2 and the 1/2 cancel. We get, and then we're just gonna compute this, right? We plug in 0 and we subtract. So we get 2 square root of 5, right? So 2 squared is 4 plus 1 is 5. So square root of 5 plus the natural log of 2 plus the square root of 5 minus, and then I get a 0 term here because it's 0 times something, plus the natural log of 0 plus the square root of 1. Okay. Now, just to clean it up a little bit, because I want to clean this up. So I'm subtracting, this 0 goes away. Natural log of, this is the natural log of 1, right? So 0 plus the square root of 1 is just 1. What's the natural log of 1? Yeah, it's 0. So the natural log of 1 is 0 because e to the 0 is equals 1. So that's all 0. And so we end up with this. That there's our final answer. Okay. Cool. Okay. Any questions on that? How am I doing on time? Okay. Okay. Let's go ahead and move on to the next example here. Okay. So another path, this one lives in 2-dimensional space. And this one's actually a little more interesting. And if you look at this path, it should look familiar. And we'll talk about that after. But let's start by just, if you saw this and you just needed to compute it, how would you do it? You'd say, okay, well, I have my formula. Let me start by taking some derivatives. So x prime of t is negative sine of t, and y prime of t is cosine of t. Okay, so you have these two derivatives. We can use that in our formula. So the length of c is the integral from 0 to pi. So we're using this interval here, 0 to pi, of the square root of negative sine of t squared plus cosine of t squared dt. Something nice is actually happening here. If I take a negative squared, the negative goes away. And so I get the square root of sine squared t plus cosine squared t dt. Okay, something nice is happening here now, right? What is sine squared of t plus cosine squared of t? Yeah, it's just 1, right? This is one of your trig identities, right? If you didn't remember that trig identity, then that makes this a lot harder, right? But this is just 1. And so the integral of 1, right? This no longer depends on t, so it's just the integral of 1. So that's just t from 0 to pi. Okay. So the length here was pi minus 0, which is just pi. Okay. So something interesting happened here. We ended up, because we had cosine and sine, we ended up taking, some kind of cosine, we ended up taking some kind of sine squared, cosine squared. So our antiderivative just ended up being t. And so the length here of this curve, no matter what the interval is going to be the end point minus the starting point in terms of time, right? So let's pause for a second before we move on to the next example and think about, why is this happening for this particular example? Well, what is this curve? What kind of path does it, or this path kind of leaves a certain picture? What does the graph of that look like? What shape does the graph of that make? I have cosine of t, sine of t. should look familiar from when we were talking about paths and curves. Want to remember? It's cosine t, sine t. Yeah, it's a circle. So it should look like a circle. Not just any circle, a circle of radius 1, right? Because if there's coefficient 2 in front of both of them, then it'd be a circle of radius 2, so on and so forth. But basically, for any value of t, you have x squared plus y squared equals 1. And for any value which is on the circle, you can find some t, which makes this true. And in fact, this is exactly how you get a point from its angle. You plug the angle in here. So if you're thinking of t in terms of time, then not only is the graph of this a circle, it's moving counterclockwise around the circle, right? Because t equals 0 is here, then t equals 1 is somewhere over here, t equals 2 is somewhere over here, t equals pi is here. We're going around this way, because as t increases, then the angle is getting bigger, so we're going counterclockwise. Not only that, but if t is measured in seconds or whatever, then you can think that we're going around the circle 1 radian per second, right? Or whatever unit of time t is measured in, okay? If we're going 1 radian per second, then however many seconds we travel, that's how many radians we've traveled, right? And so in this case, we went from 0 to pi. So we went from, we started here. This is t equals 0. And we ended here, t equals pi, okay? So we went all the way around here. And if you remember how radians work, right? 1 radian on the unit circle, if you travel 1 radian, this is 1 radian, then the arc length here is 1 unit. That's the definition of a radian. The radian is the angle so that the arc length on the unit circle is 1 unit, okay? And so if we go from t equals 0 to t equals pi, then we've traveled pi radians. So of course the arc length here is pi, okay? So that's why this formula works out the way it is. Okay, and in fact, if we'd done like t goes from, I don't know, 2 to 7, then the arc length would just be 5 because we've traveled 5 radians. Cool. Does that make sense? And if we'd gone 2 pi, then we've gone all the way around the circle, so you get the circumference, which in this case is 2 pi. Cool. Any questions on this example? So let's look at my last example. So this example here, this example here, and now one last example here. So we have this path. This time the path is in 3-dimensional space, so it's a little more complicated. This one is set up as a word problem, but it's not any more difficult. It's like a particle is flying around a room and it's following this path in 3-dimensional space, and how far does it travel during this interval? Okay, but yeah, this is not any harder than the last problem, except have 3 or the last 2 problems. Have 3 coordinates, and it's set up as a word problem, but it doesn't really matter. And we can just proceed the usual way. So we compute the derivatives of the coordinates. So we have x prime at t, which in this case is going to be -2 sine of t. And then we have y prime at t, which is just going to be 2t. And then we have z prime of t, that should be a t, which is going to be 2 cosine of t. Cool. Excuse me. Okay, so we compute the length of this curve the same way again, using that same formula. So we get the length of the curve, L of c, is the integral from 0 to 3. The 0 to 3 is coming from the interval here. of the square root of -2 sine of t squared plus 2t squared plus 2 cosine of t squared dt. This one looks scary, but it also, I'm noticing something that we saw in the last one as well, which is that we can, or I guess first thing we can do is what we saw in the first example, which is separate this 4. So there's a factor of 4 in each of these terms. So you get -2 squared, which is 4, 2 squared, which is 4, and 2 squared, which is 4. And so you get 4 times sine squared of t plus t squared plus, there should be a squared there, plus cosine squared of t. And all of this is under the square root dt. Now this next step, I'm going to do a couple of things. First of all, the square root of 4 is just 2, so I'm going to move that out of the integral. And then the next thing I'm going to notice is that sine squared of t plus cosine squared of t is just what? That trig identity, that Pythagorean identity coming up again. So the square root of 1 plus t squared. Well, we've already seen this in action. This is just going back and using that simple formula, that simple, not simple, but this given integral that we were given here. It's also given in the homework, and like I mentioned here in purple or pink, if it comes up, if an integral comes up on an exam or something that is maybe more complicated, then I will give you an integral formula for it. Okay, so in this case, this tells us that we have, again, 2 times 1/2 times t square root of 1 plus t squared plus ln of 2 of t plus square root of 1 plus t squared. And this is going from 0 to 3. Again, we have this 2 and 1/2 business canceling out. And so we get 3 square root of 10. So that square root of 10 is coming from 3 squared plus 1 plus the natural log of 3 plus square root of 10. I don't need this anymore. And then I can do minus 0 here plus the natural log of 0 plus 1. Again, this is going to go away. And so we end up with 3 square root of 10 plus the natural log of 3 plus the square root of 10. And that there's your final answer. Okay. Excuse me just 1 second, and I'll take questions. Okay, I'm back. Okay, any questions on this? So this is kind of, there are similarities to both of the examples I did. You have the trig stuff happening with sine squared plus cosine squared, and then we have to use that weird formula, and then we just plug in and it all simplifies nicely. Okay, cool. Yeah, so this section's not too bad. It's just this one concept of arc length, and it's just brushing up on the integration, and it's not even super hard integration, especially if you're given this formula right here. Okay, cool. I mean, I could take time to show you this formula and why it's true, but I don't think it's really worth it for this class. But again, if you're into a challenge, you can prove it using integration by parts. It also involves another trick from integral calc where you do the integration by parts. I think you end up doing 2 integrations by part, and then you end up with another copy of this on the other side, and you have to move it. It's kind of a weird one, but you can give it a try if you'd like. Okay, so that's the end of this section 4.2. So we can go ahead and get started on 4.3 here. Let me change that and open up that section. Yeah, so we're going to be a little bit ahead here, which is good because there's more time next week to review. So today in this section we're going to talk about vector fields, which as you can imagine from both the name and this little picture here is like a field of vectors. So you can see here we kind of have, we don't just have one vector, we have vectors everywhere, and they kind of right, they do kind of, it kind of looks like they're kind of doing something kind of in unison, right? So like this, if we're down here, it's kind of pushing this way, and then as we move further to the right, it starts angling up, and as we move up, they get longer, and so you kind of have something moving this way. They come up in some practical applications of this for things like studying like wind patterns and wind forces and stuff like that. Now I should mention before I jump into this in terms of your homework or in terms of the quizzes and stuff, we probably won't get through this section today, so don't expect 4.3 and 4.4 to show up on the worksheet and quiz next week. So the worksheet and quiz will just cover up to 4.2. So I guess 3.3, I think, to 4.2. Okay. Cool. So let's give a definition here. So formally speaking, a vector field is a map from n-dimensional space to n-dimensional space. But this is not how we want to think about it, because as you saw from like, this doesn't immediately show you how it's related to that picture I showed before. But basically what we can think is that vector fields are a way of thinking about maps in this form. In other words, right, so we've said that, you know, if n is equal to 2, then you have a map from R2 to R2. You can't really draw a graph for that, right? Because it would live, the graph would live in 4-dimensional space because you have 2 inputs and 2 outputs. So you'd have 4-dimensional space. But what this does is it gives us a way to picture what this graph is doing without actually drawing a graph. So for example, we can say, what do I want to say? The inputs, we can think of the inputs as points and the outputs as vectors based at that point. So what does that mean? So if we have a point here, so say this is xy, then f of xy, we can draw it as a vector based here. So this here is the f of x comma y. Okay. And we're going to see some examples here in just a second of how we can go about drawing problems like this, or sketching vector fields like this. Okay. Okay. So again, what we're thinking of this map, you know, we'd say it's just a map from Rn to Rn, but the way we're thinking about it is the input is telling us, okay, we're looking at this point here, okay? The output is telling us what's the vector based at that point, okay? And that's how we can get a drawing like the one we saw before, right? At this point, we get this vector. At this point, we get this vector. At this point, we get this vector, and so on and so forth. So it's assigning at every point we get a vector, okay? Yeah, so I should write that down. So it's an assigning a vector to every point. So it's an n-dimensional vector to every point in Rn. Okay, so let's jump into some examples here. So we're going to sketch some vector fields. And I might not be able to fit all of these on one slide, so I'm going to move these out of the way for now. Start with this one here. So what is this doing? This is saying, notice there's no x's and y's in the output here. So what this is saying is for every input, so this doesn't depend on x and y. So every input has the same output. So how would I go about sketching this? So what you do is I'm going to set up my coordinate grid. Now on the homework, the way they do this is because it's an online homework. It's like more of a matching thing. It's like, here are 3 vector fields and here are 3 graphs. Which of these graphs go with each other? Okay. Which of these graphs go with the formulas for the vector fields? Okay. So what we're doing is we're saying, okay, let's just pick some nice points. We can't draw the vector field at every point because they're like infinitely close together and then they keep going out infinitely, but we can pick a nice little grid here. So here at the origin, right, the output is 0, 1. So we draw a vector which is 0 in the x direction and 1 in the y direction. So we have something like this. Okay. And then if we move over by 1, well, it's the same exact vector as output. So what the output is here is a vector that's just straight up of unit length at every point. So it's just this kind of vector. So if we're thinking of vector fields as like wind direction and wind speed, or wind velocity, right? Then this would just be if you just had a perfect breeze going at the exact same speed everywhere, just in one direction, just kind of pushing along. Okay, or I guess pushing up in this way. Okay, and then you can kind of draw all of these. Drawing them can get kind of tedious because I got kind of ambitious here with how far to the right and left it goes, but kind of keep this going. I think you get the picture. Speed it up here. So drawing these by hand can get kind of tedious. There are tools online that can graph vector fields for you. Unfortunately, like Desmos and GeoGebra don't have something built in so that you can easily draw them. There are, if you Google like Desmos or GeoGebra vector fields, there are people who've built tools around them that can do it, but it's not just out of the box. So it does take a little bit more work. So now let's do one that's a little more interesting. So that first example was a constant vector field. Is that the right word? Yeah, it's constant because it's at every point you get the same vector out. And so it's doing the same thing everywhere. Okay. So now if we think of this vector field here, which is the input, if you give a point, it ignores the x output. So it's not going to depend at all on the x value, but the y value is going to become the x value of the output of the vector. So let's see what that looks like. So let's draw a graph here, or a blank slate here. Okay. Okay. Blue here. Okay. So at 0, 0, if the input is 0, 0, then we get the 0 vector here, right? 0, 0 gives us 0, 0. And in fact, if we plug in anything with y value 0, we're going to get the 0 vector as output. So all along here, we just get the 0 vector as output like that. Okay. Because if we plug in anything with y equals 0, then we get 0 vector over here. So now if we go up by 1, so if we're here, right, now at this point, the y value is 1, and so the x value of the output is going to be 1. So this is 1 comma 0, sorry, no, 0 comma 1. So the output is 1 comma 0 as a vector, so it's something like this. And that's going to be the case everywhere along this horizontal line. So we get something like this. Okay. Now, what if we go up here? If we go up here, right? So now the y value is 2. So that means that we go 2 in this direction. And so these vectors are now twice as long. And so I'm going to not draw as many of them, but you can kind of get the idea. Okay. So the vectors are twice as long. You can imagine that if we were up here, they'd be, so like I'll draw one up here, maybe a couple up here. Okay. So they're getting longer and longer as you go. They're always pointing it to the right, but the further you go up, then you can the further the kind of the longer they are. So if we're thinking of these again as like the velocity of wind, right? If you're standing right here, then it's kind of not it's not moving you at all. The wind is not blowing at all right along this line. But if you move up a little bit, then it's kind of blowing you a little bit this way. So like there are a lot of vectors that I'm not drawing here. So for example, like here, it would be a nice little short one in this direction. Here it would be somewhere like that. So there's a lot in between that I'm not drawing. But basically, as I move further up, the wind gets stronger and stronger in the rightward direction. Okay. And section 4.4 is actually a couple of tools having to do with vector fields that we can actually use to think about this and kind of take these analogies a little further, the real world analogies here. Okay. And now what happens if we move down? One thing we haven't drawn here is what happens if we move down. So if I put this point here, then y is now equal to -1. So we get in the x direction, we get a negative number. So we're pointing to the left here. So we actually get a picture that looks like this. Okay. So we get basically the same thing, but kind of pointing in the opposite direction. So I think here it's twice as long. On this level, it's twice as long. So on and so forth. Okay. Cool. Maybe I'll draw one more. Okay. So again, if I'm thinking of this as wind, then if I'm right here, there's no wind blowing. But if I move up a little bit, I go to the right. But if I move down a little bit, I move to the left. Okay. Cool. Cool. Oops. One last example here, which I'll give myself a little extra room here. So in this case, it looks like it's not doing anything, right? The input just gives me the output, but how do we draw that? So again, I'm going to give myself a blank graph here. Give myself plenty of room. Okay. I'm going to move this down here. Okay. So this blank graph. So at the origin, it seems like a good place to start. So at 0, 0, we get 0, 0. What about at 1, 1, 0? Well, now that gives us just this vector here. What about at 0, 1? Well, we get this vector here. All of these, kind of nice. And now as we get further away from the origin here, for example, if I plug in here, this is 2, 0. Well, now I'm going to get a longer vector, so twice as long here. Okay. Now, what if we put something that's not on the axis? So what if we plug in this value here? This is 1, 1. So we get something that looks like this, right? Because it goes up 1 and over 1, or over 1, up 1, however you want to see it. So over 1, up 1. Something like this, a point here is 2, 1, 2. So it's over 1, up 1, 2. So it's slightly steeper. So basically, as we move up, it's getting even steeper and longer. Over here, something like this. Here, you'd get something like this, right? So the point is that as you move out, basically what you're getting is you're getting vectors that always point out, but they get longer the further you go out. Okay. So I'm getting rougher and rougher with my sketching because it's just a little easier to draw that way. Oops. So, nope, that's not right. Okay. Okay, cool. Any questions on this? So if you're doing this on the online homework, you're in that, like I said, in that case, it's more of a matching thing. It gives you the graphs. It doesn't necessarily ask you to, you don't have to draw anything, right? But if you're asking like, okay, how do I check? Well, check a few points. So check what happens at the origin. Well, according to this, the origin should be the 0 vector. If you see the 0 vector on one of the graphs, then you say, okay, that could be it. That could be the match, right? If there's only one graph that has the 0 vector right at the origin, then that has to be the one, right? And you can do the same thing with, just compare a bunch of them. Some of them it might be in 3D, so those would be a little harder because you have to move around. But I don't remember seeing any that were explicitly in 3 dimensions, but I'm not 100% sure on that. Okay, cool. I think for the sake of drawing and stuff, putting things in 3D or 2D is probably easiest. So for part B, y equals 0 means the vector field is always drawing horizontally, and x equals y controls the length of the vector. So it gets confusing. We can think of the x and y as the inputs. Maybe we can call this like the I coordinate, the I and the j here. So the fact that j equals 0 means, or that you have a zero on j means that it's always horizontally. We're always going horizontal because there's a j. The j coordinate is 0, and then because the I coordinate is y, that means that the height of our point is determining, like you said, the length, but also the direction. So if it's positive, it goes to the right. If it's negative, it goes to the left. And then just the absolute value is the length of this vector. But yeah, right idea. The fact that we have a 0 here means we're going horizontally. The fact that we have a y here means that the y value, the height, determines the length and the direction. Okay, cool. Any other questions? So it's kind of an acquired skill, graphing these things. Like it's not always like this vector field is one I've seen enough that I already knew is going to look like this. But there are vector fields you could show me, and I would not necessarily off the top of my head know exactly how they look. But you could just start graphing some of them. Just start graphing some points, some nice points. The origin, what happens along the axis, what happens, along certain lines and stuff like that. Okay. Yeah. Yeah, I think I have time. Maybe I'll do that instead of moving on. Do that. Another example. Come on. So got asked in the chat, what if we, so maybe I'll write this in this part D. What if we had f of xy equal to y comma x? So I think I know what that's going to look like, but let's see what happens. Let's just work through it. So as if we were seeing it for the first time. So we have our x and y axes. Okay. And what we're going to do is we're going to say, okay, what happens at the origin? Well, at the origin, it's still 0, right? Okay. So now what about along this x-axis? So as we go along the x-axis, right? So for example, at 1, 0, 1 comma f of 1 comma 0 is going to equal 0 comma 1. So we're here, but we're pointing straight up. Okay. And if we did f of 2 comma 0, 0, we'd get 0 comma 2. And so we'd get something like this. So as we move further out, if you can tell, what's happening is we're doing something like this. The x-axis, and then if we went negative, these would be negatives, and so we'd be pointing down. So we get something like this, kind of in the opposite direction. Okay. Now what happens on the y-axis? Well, on the y-axis, so for example, f of 0, 1 is going to give us 1, 0. Oh, so it's actually a little different than I thought it was going to be, but this works. So at 1 comma 0, we get something like this. You can imagine that at 2 comma 0 or 0 comma 2, we'd get something like this. So they're all kind of meeting up with these. Okay, and then in the negative, we'd get something like this. Okay. Okay. So this is just what's happening along the axis. What's happening in here? So I'll save you some trouble, but along the diagonal here, it's going to be straight up. Okay. Now, one thing about these is that if you haven't noticed, is that these should be continuously like moving towards each other, right? So like if we follow a point, if we move the point a little bit, the vector shouldn't change too much. So over here, as the point moves from here to here, the vector's just kind of rotating like this. Okay. But here it looks like how do I get from here to here? And how do I get from here to here, right? So if we looked at the points in between, so for example, like a point like here, this is 2 comma 1, f of 2 comma 1. This is going to equal 1 comma 2 as a vector, so 1 comma 2. So this is kind of getting something like this. And so we actually get this kind of stuff happening like, and it gets kind of hard to draw, but we can kind of see that it like becomes kind of angled until it straightens out like that. So we get kind of these points in between that kind of angle until they show up like this. Same thing going this way. That's curved. That's not how vectors work. Okay, so it's kind of these. So basically, I'm mirrored. So you have your x and y axis. The vectors are like this, but as you get, and then along the diagonal, they're just perfectly up and to the right. And so what happens is as you get closer to that diagonal, the angle of the vectors is changing until they line up like this. So it's like that, something like that. The vectors are doing it. The picture is kind of hard to draw. I think maybe the slightly more interesting question is what happens in these. So something similar would happen down here, right? What's happening over here? So for example, what's at 1, -1? So f of 1, -1 becomes -1, 1. So -1 the x direction and 1 in the y direction. So we actually get something like this. And in fact, what's happening here is we get these sort of vectors looking like this, which is harder to look at than these vectors. But basically, as we get further, they're longer and longer, and they're being drawn toward the origin. Oh, that should be longer. Yeah, so it gets kind of messy. The drawing here gets kind of messy. And then something similar is happening over here. If we go this way, then we're kind of getting more angled and getting drawn more and more towards the origin here. So the graph of this one got kind of messy, but it kind of, you have these kind of, if you're along this line, you're kind of going away from the origin. If you're along this line, you're kind of going towards the origin, and everything in between just kind of smoothly flows between those. Okay. So I'm low on time, or I'm out of time. But if you want to practice one, for practice, I think a slightly nicer one is, and I'm going to forget it off the top of my head, is f of x, y is equal to see, it should be -y comma x. Okay. So try this one on your own and see what you get. This one will be it doesn't look much different than this one, but the sketch ends up being nicer.